Connecting two grounding transformers to the same 33 kV ungrounded system at the same time is generally not advisable. There are several reasons for this recommendation. Firstly, circulating currents are a major concern. Connecting two grounding transformers in parallel creates a closed loop. This closed loop provides a path for circulating currents to flow through the ground. The circulating currents can cause excessive heating in the grounding transformers and other equipment connected to the grounding point. This overheating can lead to premature failure of the equipment. Secondly, there is a risk of increased fault current. If a fault occurs on the ungrounded system, the presence of two grounding transformers provides two parallel paths. These parallel paths allow the fault current to return to the source. This could increase the overall fault current magnitude. The increased fault current may cause the system protective devices to trip prematurely, potentially disrupting operations. It is important to understand the difference between zigzag transformers and grounding transformers. The zigzag transformers connected to the 33 kV bus serve a different purpose than grounding transformers. Zigzag transformers are primarily used for voltage stabilization. They do not provide a direct path for fault currents to return to the source like grounding transformers do. Therefore, zigzag transformers do not inherently create a risk of circulating currents in the system when used for voltage stabilization. Regarding the parallel operation of the 250 MV 220 kV by 33 kV transformers, these can generally run in parallel. This is possible because they have the same voltage ratio and phase displacement. However, it is crucial that these transformers are equipped with protective relays. These protective relays are designed to detect any imbalances in voltage or current. Such imbalances could indicate a fault condition or other abnormal operating scenarios. If a fault is detected, the protective relays will act to isolate the faulty transformer from the system, preventing further damage. The choice of whether to use one or multiple grounding transformers in a system is a critical design consideration. It depends on several factors, including the size of the system, the expected fault current levels, and the desired level of protection. In many cases, a single grounding transformer is sufficient to provide adequate protection against ground faults. However, in some situations, multiple grounding transformers may be necessary. This might be the case if the system is very large or if there are multiple sources of power. When considering multiple grounding transformers, careful coordination and protection schemes are essential. This is to prevent the issues associated with circulating currents and increased fault current levels that were discussed earlier. Grounding transformers, also known as neutral grounding transformers, are specialized transformers used to provide ground reference in ungrounded or impedance-grounded power systems. Their primary purpose is to limit the magnitude of ground fault occurrence, thereby protecting equipment and personnel from damage and electrical shock hazards. In an ungrounded system, there is no intentional connection between the system's neutral point and the earth. While this might seem like a disadvantage, ungrounded systems can actually continue to operate during a single ground fault. This is because the fault current is limited to the capacitive charging current of the system. However, this benefit comes with a significant drawback. The voltage on the unfaulted phases can rise to dangerously high levels, potentially damaging equipment. Furthermore, a second ground fault on a different phase can result in a severe phase-to-phase fault, causing extensive damage. Grounding transformers address these issues by providing a low impedance path for ground fault currents to flow. This limits the voltage rise on the unfaulted phases and allows protective devices to quickly detect and clear ground faults. Grounding transformers come in several different configurations. The most common types are zigzag transformers and Y-delta transformers. Zigzag transformers are specifically designed for grounding purposes. They have a unique winding configuration that allows them to provide a low impedance path for zero-sequence currents, which are the currents that flow during ground faults. Y-delta transformers can also be used for grounding, but they are not as effective as zigzag transformers in limiting ground fault currents. In a Y-delta transformer, the Y winding is connected to the system neutral, and the delta winding is typically left ungrounded. During a ground fault, The fault current flows through the Y winding and into the delta winding, where it is dissipated as heat. The impedance of the delta winding limits the magnitude of the ground fault current. The selection of a grounding transformer depends on several factors, including the system voltage, the expected fault current level, and the desired level of protection. It is important to choose a grounding transformer that is properly sized and rated for the application. Oversizing the grounding transformer can lead to unnecessary costs, while undersizing it can result in inadequate protection. In addition to providing a ground reference, grounding transformers can also be used to reduce voltage transients and improve power quality. Voltage transients are sudden surges in voltage that can damage sensitive electronic equipment. Grounding transformers can help to dampen these transients by providing a low impedance path for them to dissipate. Power quality refers to the stability and reliability of the electrical power supply. Grounding transformers can help to improve power quality by reducing voltage imbalances and harmonic distortion. Voltage imbalances occur when the voltages in the three phases of a power system are not equal. This can cause equipment to overheat and fail. Harmonic distortion is the presence of unwanted frequencies in the power supply. This can interfere with the operation of electronic equipment. Grounding transformers can help to mitigate these problems by providing a path for the unbalanced currents and harmonic currents to flow. The installation and maintenance of grounding transformers are critical for ensuring their proper operation and safety. Grounding transformers should be installed in accordance with all applicable codes and standards. It is important to ensure that the grounding transformer is properly grounded and that all connections are tight and secure. Regular maintenance should be performed on grounding transformers to check for signs of wear and tear. This includes inspecting the windings for damage, checking the oil level, and testing the insulation resistance. Any problems that are found should be repaired promptly. Grounding practices are essential for ensuring the safety and reliability of electrical power systems. Grounding provides a low impedance path for fault currents to flow, protecting equipment and personnel from damage and electrical shock hazards. There are several different types of grounding systems, each with its own advantages and disadvantages. The most common types of grounding systems are solid grounding, impedance grounding, and ungrounded systems. Solid grounding is the simplest and most common type of grounding system. In a solid grounded system, the neutral point of the power system is directly connected to the earth. This provides a very low impedance path for fault currents to flow, resulting in high fault current levels. Solid grounding is typically used in low voltage systems where the risk of electrical shock is high. Impedance grounding is a type of grounding system in which an impedance, such as a resistor or reactor, is inserted between the neutral point of the power system and the earth. This impedance limits the magnitude of the ground fault current, reducing the risk of damage to equipment. Impedance grounding is typically used in medium voltage systems where the fault current levels in a solid grounded system would be too high. Ungrounded systems, as mentioned earlier, have no intentional connection between the system's neutral point and the earth. While ungrounded systems can continue to operate during a single ground fault, they also have several disadvantages, including the risk of overvoltages and the potential for a second ground fault to cause a severe phase-to-phase fault. The choice of grounding system depends on several factors, including the system voltage, the expected fault current levels, and the desired level of protection. It is important to carefully consider these factors when selecting a grounding system. Protective relays are essential components of electrical power systems. They are designed to detect faults and other abnormal conditions and to initiate the tripping of circuit breakers to isolate the faulty equipment from the system. Protective relays are used to protect a wide range of equipment, including transformers, generators, motors, and transmission lines. There are many different types of protective relays, each designed to protect against specific types of faults. Some common types of protective relays include overcurrent relays, overvoltage relays, undervoltage relays, differential relays, and distance relays. Overcurrent relays are used to protect against overloads and short circuits. They operate when the current in a circuit exceeds a predetermined level. Overvoltage relays are used to protect against overvoltages. They operate when the voltage in a circuit exceeds a predetermined level. Under-voltage relays are used to protect against under-voltages. They operate when the voltage in a circuit falls below a predetermined level. Differential relays are used to protect transformers, generators, and other equipment against internal faults. They operate by comparing the current entering and leaving the equipment. If there is a difference between the two currents, it indicates an internal fault. Distance relays are used to protect transmission lines against faults. They operate by measuring the impedance between the relay and the fault. The impedance is proportional to the distance to the fault. The settings of protective relays are critical for their proper operation. The settings must be carefully selected to ensure that the relays will operate quickly and reliably when a fault occurs. The settings must also be coordinated with the settings of other relays in the system to prevent nuisance tripping. Nuisance tripping occurs when a relay trips unnecessarily, disrupting the operation of the system. The coordination of protective relays is a complex task that requires a thorough understanding of the power system and the characteristics of the relays. Protective relay coordination studies are typically performed by experienced engineers. These studies involve analyzing the power system to determine the optimal relay settings and ensuring that the relays will operate correctly under all operating conditions. Power quality is a measure of the stability and reliability of the electrical power supply. Poor power quality can cause equipment to malfunction, overheat, and fail. There are several different types of power quality problems, including voltage sags, voltage swells, voltage transients, harmonic distortion, and voltage imbalances. Voltage sags are temporary decreases in voltage. They can be caused by faults, motor starting, and other events. Voltage swells are temporary increases in voltage. They can be caused by switching operations and lightning strikes. Voltage transients are sudden surges in voltage. They can be caused by lightning strikes and switching operations. Harmonic distortion is the presence of unwanted frequencies in the power supply. It can be caused by nonlinear loads such as electronic equipment and adjustable speed drives. Voltage imbalances occur when the voltages on the three phases of a power system are not equal. They can be caused by unbalanced loads and faults. There are several different ways to improve power quality. Some common methods include using surge suppressors to protect against voltage transients, using harmonic filters to reduce harmonic distortion, and using voltage regulators to maintain a stable voltage. Power factor correction is another important aspect of power quality. Power factor is a measure of how efficiently electrical power is used. A low power factor indicates that a significant portion of the electrical power is being wasted. Power factor correction can be achieved by using capacitors to compensate for the inductive reactance of electrical loads. Inductive reactance is the opposition to the flow of alternating current caused by inductors, such as motors and transformers. The NEC, or National Electrical Code, provides guidelines for grounding and bonding electrical systems to ensure safety. Article 254 of the NEC addresses general requirements for grounding and bonding. It emphasizes the importance of creating a low-impedance path for fault currents to facilitate the operation of overcurrent protective devices. The NEC also covers specific requirements for grounding different types of equipment, such as transformers, generators, and motors. Table 250.122 in the NEC provides guidance on sizing equipment grounding conductors. This table specifies the minimum size of the equipment grounding conductor based on the rating of the overcurrent protective device in the circuit. Proper grounding and bonding practices are essential for preventing electrical shock hazards and minimizing the risk of fire. It is important to follow the NEC guidelines carefully when designing and installing electrical systems. Always consult with a qualified electrician or electrical engineer if you have any questions about grounding or bonding. In summary, the NEC provides comprehensive guidelines for grounding and bonding electrical systems, and following these guidelines is crucial for ensuring the safety and reliability of electrical installations. Ground fault circuit interrupters, known as GFCIs, are life-saving devices that protect people from electrical shock. They work by monitoring the current flowing in the hot and neutral conductors of a circuit. If there is a difference of 5 milliamps or more between the current flowing in the hot and neutral conductors, the GFCI will trip, interrupting the circuit and preventing an electrical shock. GFCIs are required in many locations such as bathrooms, kitchens, and outdoor areas where there is a high risk of electrical shock. They are also recommended for use with portable tools and appliances. GFCIs are relatively inexpensive and easy to install. They are an essential safety device for any home or business. Surge protective devices, called SPD, are designed to protect electronic equipment from voltage transients and surges. They work by diverting the excess voltage to ground, preventing it from damaging the equipment. SPD are available in a variety of types and sizes, including whole-house surge protectors, plug-in surge protectors, and hardwired surge protectors. Whole-house surge protectors are installed at the electrical panel and protect all of the equipment in the house. Plug-in surge protectors are plugged into an electrical outlet and protect the equipment plugged into that outlet. Hardwired surge protectors are hardwired into the electrical system and protect specific equipment. SPD are an important investment for protecting sensitive electronic equipment from damage. Regular inspection and testing of grounding systems is important to ensure that they are functioning properly. Grounding systems should be inspected visually for signs of corrosion or damage. Ground resistance testing should be performed periodically to measure the impedance of the grounding system. If the ground resistance is too high, it indicates that the grounding system is not functioning properly and needs to be repaired or replaced. There are several different methods for measuring ground resistance, including the 3-point fall-off potential method and the clamp-on ground resistance meter method. The 3-point fall-off potential method is the most accurate method for measuring ground resistance. The clamp-on ground resistance meter method is a convenient method for measuring ground resistance without having to disconnect the grounding electrode. Proper maintenance of grounding systems is essential for ensuring the safety and reliability of electrical installations. Grounding electrode systems are a critical part of any electrical system, providing a path for fault currents to flow to ground. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or underground metallic water pipes that are connected to the earth. The grounding electrodes must be installed in accordance with the NEC guidelines to ensure that they provide a low impedance path to ground. The size and type of grounding electrodes required depends on the size of the electrical system and the soil conditions. The NEC provides specific requirements for the size and type of grounding electrodes that must be used in different situations. The grounding electrode conductor connects the grounding electrode to the electrical system. The grounding electrode conductor must be sized in accordance with the NEC guidelines. The size of the grounding electrode conductor depends on the size of the electrical system and the type of grounding electrode. The grounding electrode conductor must be made of copper or aluminum and must be protected from physical damage. Bonding is the process of connecting together all of the metallic parts of an electrical system to create a low impedance path for fault currents to flow. Bonding helps to prevent electrical shock hazards and minimizes the risk of fire. All metallic parts of an electrical system, including conduit, enclosures, and equipment, must be bonded together. The bonding conductors must be sized in accordance with the NEC guidelines. The size of the bonding conductors depends on the size of the electrical system and the type of equipment being bonded. The bonding conductors must be made of copper or aluminum and must be protected from physical damage. Effective grounding and bonding practices are essential for ensuring the safety and reliability of electrical installations. In conclusion, when dealing with 33 kV ungrounded systems, avoid connecting two grounding transformers simultaneously to prevent circulating currents and increase fault current. Understand the distinct roles of zig-zag transformers for voltage stabilization. Equip parallel transformers with protective relays to detect imbalances. Adhere to the NEC guidelines for grounding and bonding, and regularly inspect and test grounding systems for optimal safety and performance.